Welcome back. Section 6 in Chapter 19 is the Friedel-Crafts Acylation. So once again, it was devised by Friedel-Crafts. Remember that there were a number of different rearrangements that limited the Friedel-Crafts alkylation. So Friedel-Crafts overcame that with the acylation reaction. Now, when you have an aromatic ring like benzene attached to a boryl propyl group, this is called an alkyl group. Okay? We abbreviate it in chemistry class as an R group, and that can be methyl, ethyl, propyl, butyl, iso, pentyl, whatever, cyclo, hex, any kind of alkyl group without double bonds, and just, it could be the whole rest of the molecule. Now, these molecules like acetophenone, for example, notice how the name is aceto. You have that AC in there. This is an acyl group. An acyl group is the carbon-oxygen double bond along with the R group to the right. So the abbreviation for this would look like this. Okay, and that R group could be anything to your heart's desire, okay? Now, the way this is synthesized is through a very similar manner. We treat the benzene, or the aromatic starting material, with an acid chloride, okay? Okay, and there's no rearrangement. Okay, let me take you through the curved arrow reaction mechanism here. So let me just highlight first of all that this functional group is a derivative of a carboxylic acid, and we call these acid chlorides. Okay. Okay. Propanoyl chloride would be the technical IUPAC name for this. You won't learn that until chapter 20 or something. All right. So how does this reaction work? So first of all, we have a chlorine there, and just think chlorine has an affinity for aluminum trichloride, and that would be a good thing to guess, and that's what we draw here, okay? So aluminum trichloride is this nice Lewis acid, kind of lacking an octet if you want to think about it that way, and so these electrons from chlorine attack it, and you form a Lewis acid base complex. And what we do here is we immediately kick off the leaving group. The leaving group here is highlighted in yellow here. Okay, and so we want to use these lone pairs on oxygen, and we want to kick off the chlorine. Okay, when that happens, I'll draw it bent like this, but when you do that, you have a carbon triple bond, and then you have a positive charge on that oxygen atom, and you have chlorine, right here, attached to the aluminum trichloride, and that's in equilibrium with chloride and aluminum trichloride, okay? So what we have at this point is this guy here, which is your electrophile. And they have a special name for that. That's called the Acelium Ion. It's not really a carbocation, but we can draw it as such. So the Acelium Ion if we use some resonance arrows to show how it's stabilized. And I'll draw in a different bent, which I really shouldn't, but I'll just do that since I think it's easier or more comfortable for students to see it in kind of this structure. But this right here is a positively charged thing, so it's an electrophile, right? It's called the Acelium Ion. Okay, special name for it. Okay. And if you look at the structure on the right, it looks like a carbocation. But because its resin is stabilized by the oxygen right next to it, it doesn't need to rearrange. It's as stable as it can be. It looks weird, it looks strange, it makes a lot of students uncomfortable, but that's what we need to draw. You can use either resonance structure in your mechanisms, the one on the left or the one on the right. I like to use the one on the left, okay? So now what we do is we take benzene and we attack the Acelium ion. So again, I'll draw this hydrogen in here. And be careful when you draw your Acelium ion. Make sure that has the right number of carbons, okay? In my structure, I had 3 carbons, so I have 3 carbons here, okay? And I'm gonna put a plus on this oxygen. And so now when these pi bonds come in and attack this carbon, again, the electrons flow towards the more electronegative atom, and that's the attack step. And we get a carbon-carbon bond formation here. I'll draw in the C so we can see it clearly. And you want to make sure you have the right number of carbons. 3 carbons there. Okay, so everything else looks familiar at this point. And so that's a new carbon-carbon bond, okay, to a ketone, okay, to an acyl group. So now at this point, chlorine's going to snag this hydrogen and regenerate the aromatic ring through deprotonation. Okay. All right, so that's pretty cool. We've installed this kind of like acyl group. Okay. So, and there's no opportunity for rearrangement. Okay. So again, that reaction is right here. Okay. We just add an acid chloride of our choosing, aluminum chloride, and we get the product. Okay. So let me show you some kind of techniques. Okay. So if you have an aromatic ring and you treat this with your acid chloride, okay, you need to be careful which 2 carbons are becoming connected. So here's benzene is perfectly symmetric. We grab any one of those carbons and we want to connect it to the acyl carbon. Count your carbons and make sure you don't drop any in the reaction, okay? So here's my benzene with my dotted carbon, and then I want to draw a line, okay? And I'm connecting it to that carbon of the acyl group. Make sure you put your double bond O, okay? And then sketch out exactly the kind of branching pattern that you have there, okay? Don't just draw a straight line because that's incorrect. We want to maintain that branching, okay? When I say no rearrangement occurs, I mean that it stays branched or it stays linear or whatever, okay? Now you also can do reactions where you add new aromatic rings to your structure. So we can do that by adding benzoyl chloride, for example. So if we add aluminum trichloride here, the product that we're going to get is one in which you have a ketone flanked by 2 phenyl rings. Okay, so this whole thing right here is being added. Okay, so that's something to think about in terms of techniques. The other thing I wanted to mention here is that you can have an internal reaction. So for example, if you have something like this, and you don't mix this molecule with anything else, you just add aluminum chloride to it, what happens is that this is your acid chloride group. okay? And this is your aromatic group. Now, because of the ring strain and things like that, this nicely just forms like that up where that second carbon is that I've highlighted in yellow, okay? So what you form is a 1, 2, 3, 4, 5, 6-membered ring attached to your benzene ring, which also has 6 carbons. So here's carbon 1, 2, 3, 4, 5, 6, okay? Carbon 6 has the carbon-oxygen pi bond, and carbon 1 and carbon 6 become connected. If it's helpful, you can draw little dots. We know that carbon 1 is going to connect to that acyl carbon, okay? So if you like to draw dots on your molecules, that's a helpful way to keep in mind which 2 carbons are forming, okay? So that's the new CC bond, okay? Okay, so that summarizes, oh no, it does not. Now, there's also a Clemenson reduction that you can do. Okay, and this is very important because, for example, if you take benzene and you treat it with propanyl chloride, which is one of the examples I did before, this first step is called the Friedel-Crafts Acylation, and you can stick on the propanyl group there, okay? So now what you can do is you can treat this with zinc that's in a mercury amalgam, that's made from a mercury amalgam, so a mixture of zinc and mercury, not too healthy. HCl and heat, triangle is heat in my book. Then what you do is you basically reduce completely that ketone group, okay? So this is a very key reaction. You want to have that on your note card, and here's the reason why. Here's the reason why. Let's talk about synthesis, okay? How would you make this molecule right here with a straight chain butyl group? Now, if you took benzene and you treated it with chlorobutane and aluminum trichloride, remember again that this is a limitation. You would expect major amounts of a rearranged product that goes through a secondary carbocation, and you would expect only very minor amounts of the straight chain butyl chain, okay? So that is not a good reaction. Instead, what we would need to do is to take our aromatic ring, here it's just benzene, we would need to treat this with our acid chloride that has the 4 carbons in the exact shape, here we just want straight chain, that we want, aluminum trichloride, and that would get my acyl group. And remember that there's no rearrangement. No rearrangement, so that means that's the only product I have. And then I could do this Clemenson reduction with zinc and mercury amalgam, hydrochloric acid and heat to give me the straight butyl chain attached to the aromatic ring, and that would be the only product, So that would have a much higher chance of success, okay? So keep in mind that when you're doing synthesis, think about, do you need to do a Clemenson reduction or not, okay? So that's where I want to finish up this chapter, and thanks for watching, and please subscribe if you like my channel.